Hello and welcome to this presentation related to dimensional analysis. This presentation relates to dimensions and is basically a continuation of a previous presentation. In this presentation we're going to consider some further tasks where we'll be finding the unknown exponents in given non-dimensional expressions. So for example, this is a non-dimensional expression, q to the x omega a to the y. And in this expression we'll be solving for the exponents x and y. Just for your background information, here are two other presentations related to the dimensions topic. The first was an introductory presentation where we introduced the MLT theta dimensions, stated the principle of dimensional homogeneity, and used various illustrations to show the applications of dimensions. In a separate presentation we were finding unknown exponents, but this time we were given formulae or equations to solve. So I strongly encourage you to review the two other presentations before reviewing the contents of this presentation. For reference, here's a recap slide from the initial dimensions presentation showing the SI base units. Predominantly we'll be using the length, mass and time dimensions in this particular presentation. Another recap slide here from our previous presentation, just highlighting the laws and the rules of indices. We'll be using those quite extensively within the solutions that follow, and we'll also have to solve simultaneous equations within certain solutions. So here's a brief introduction to this presentation. We're going to be given various non-dimensional expressions within the following tasks that are presented, and assuming dimensional homogeneity throughout, we've got to determine the values of the unknown exponents in these expressions. So it's important to note that each of the given expressions are non-dimensional, and so they all equate to unity, which can be written in terms of dimensions as MLT, square brackets here, to the power of 0, and using the third law of indices that can be written as m to the 0, l to the 0 and t to the 0. So that will basically form the left hand side of the equations that we're going to generate. And the table below shows the various quantities, symbols and SI units that will be used in the various tasks we're going to consider in this presentation. So we will refer to these as required when solving each of the tasks that are specified in the presentation. So task 1 shows the non-dimensional expression of acceleration, length to the power of b and time to the power of c. So in task 1 we'll be solving for the exponents or the powers b and c. Here's task 2. We have length to the power of a, viscosity and time to the power of b. So in task 2 we'll be solving for a and b. Then we have task 3, three variables again in the expression, solve for exponents x and y. And finally task 4, four variables in the expression, this time we'll solve for exponents x, y and z. And here are the approximate start times related to the various tasks contained within the presentation. On the next slide, task 1 commences, but task 2 commences 8 minutes in, task 3 11 minutes in, and task 4 16 minutes into the presentation. Please note that these times are rounded to the nearest minute. So here's task 1. So our non-dimensional expression includes a, that's acceleration, l to the power of b, that's be length to the power of b, and t to the power of c, that will be time raised to the power of c. The answer is given in the bracket here, a, l to the power of -1 and t to the power of 2. From our previously given table, here's the unit of acceleration, with length l and time 2. If you reviewed the previous presentations, you may feel that you can attempt task 2 without further assistance, so I'd encourage you to stop the presentation and do so now. So the full work solution is shown on the following slide. So task 1, here's the full solution. As always with each of these problems, firstly ensure you use the appropriate SI unit and then convert to the appropriate dimensions. So for acceleration, symbol A, that's the SI unit, meter per second squared, and in dimensions that would be LT to the -2. Next we have L to the power of B, so that's length. Length is in meters, so dimension is L. Notice we always use square brackets of course for dimensions. And finally time T, SI unit is a second, so dimension is capital T. So we know that each of these tasks relates to non-dimensional expressions. So on the left hand side, I'm essentially stating unity. That's in the form of mLt raised to the power of 0. And on the right hand side, I have my acceleration dimensions, my length dimensions raised to the power of b, of course, here, and my time dimension raised to the power of c. All that's happened on the next line is I simply use the third law of indices just to hopefully clarify the various exponents or powers associated with each of the dimensions. So on the left hand side, it's m to the power 0, l to the power 0, t to the power 0. And on the right hand side, a similar exercise. I've actually put the l to the power 1 here just to clarify that we have a 1 by default, t to the power of -2, l to the power of b, and t to the power of c. I didn't really need to add that line in, but just to try and make things as clear as possible for you when we begin to equate the indices. And that's exactly what we do now. We equate the indices related to the various dimensions we have in the task, and that allows us to generate equations. Now in this case we can generate two equations, one in terms of length and one in terms of time, but we cannot generate equation in terms of the mass because m only appears on the left hand side here. So let's first of all equate indices for length, L, the dimension L we're considering here. So on the left hand side, considering dimension L, we have L to the 0 here, so there's my 0. On the right hand side, scanning the indices associated with dimension L, we have 1, my 1, and we have B, so add my B. That can be directly solved, one unknown in one equation, so subtracting 1 from both sides, we clearly see b is equal to -1. And if we now equate indices for dimension time, t here, on the left hand side we have t to the 0, and here on the right hand side we have t to the -2, shown here, so -2, and t to the power of c, so add the c to the right hand side of the equation. Again, an unknown in one equation we can solve, so adding 2 to both sides of the equation, we clearly see that exponent c is value of 2. Now all we've got to do is state the original expression, but this time with the values of the exponents stated. So I've got two formats here, a, l to the -1, t to the +2 here, and of course from our rules of indices, l to the -1 actually means we're dividing by the l. So we could write the expression as a t to the 2 divided by l, just an alternative way of stating the expression. So that's the solution for task 1. Here's task 2, given a non-dimensional expression of L to the power of A, to length to the power of A, Greek symbol nu, that's kinematic viscosity, and T to the power of B, that would be time to the power of B. Again, for reference, the answer is shown in the bracket, so nu, T to the power of 1 here, and it's divided by L to the power of 2. Again, here's our table stating the various SI units for the quantities given. This time we have the length L, we have kinematic viscosity, nu, and time t. I'd encourage you to start the presentation and attempt task 2, but the full work solution is shown on the following slide. Task 2 is the full solution. So as always, consider the various quantities, units and dimensions. So I have L to the power of x, L, so unit in meter, dimension capital L, so length, kinematic viscosity nu, we're given the unit of meter squared per second, so dimension that's L to the power of 2, t to the -1, and we've got t to the power of y, t is time, so unit is s and dimension is capital T. So with all the tasks, this is a non-dimensional expression. So on the left hand side we have mLt to the power of 0, and on the right hand side I have my L to the power of x, my length, I have my nu dimensions, and I have my time raised to the power of y. So we can generate equations again based on L and T, cannot use m of course because m only occurs once. So equating indices firstly for the length dimension L. On the left hand side we have L to the power of 0 from the third law of indices, so 0 here. On the right hand side we have L to the power of x, so x into my equation on the right hand side. And we also have L to the power of 2, so add 2 to the equation. So one unknown in one equation, we can solve that directly by subtracting 2 from both sides of the equation. So we can clearly see that x is equal to -2, and if we equate indices for the time dimension capital T, again on the left hand side we have t to the power of 0, and on the right hand side we have t to the power of -1, so there's -1 in the equation. We have t to the power of y, so I add my y to the equation. Again, one unknown in one equation, we can solve directly for y, add 1 to both sides, we have y is equal to 1. So I can now state my solution. We have L to the power of -2, as x is -2, u is to the power of 1 of course by default, and t, I've shown that to the power of 1 here because y is equal to 1. So there's my solution. Just for reference, I could write that as nu t divided by the L to the power of 2. So the negative in the exponent means divide by. So that's a full solution for task 2. Here is task 3. We're given omega, that's angular velocity, q to the power of x, q is volumetric flow rate, and a to the power of y, a is area. Answer shown in the bracket here is omega, that's the square root of the area cubed, and that's all divided by q. So again, for ease of information, here's our table stated at the beginning of the presentation. So this time we have angular velocity omega, so the unit there is the radian per second. We have volumetric flow rate q, so the unit now is meter cubed per second, and we have the area, and that's in meters squared. I would encourage you to start the presentation and attempt task 3, but the full work solution is shown on the following slides. So task 3, here's the beginning of the solution. So our non-dimensional expression shown here, and we know from the previous slide the unit of omega is radian per second. Notice the dimension here is t to the -1. Radian is a dimensionless unit, so a value of 1, and we're dividing by seconds. So in dimension format that will be t to the -1. We have q to the x, so q is the volumetric flow rate, unit of meter cubed per second, so dimensions is L3 t to the -1, and we have area to the power of y, area is meters squared, so that's L to the power of 2. So all these tasks are non-dimensional expressions, so left hand side mlt to the power of 0, and that's equal to on the right hand side our omega dimension, the flow rate dimension raised to the power of x, and the area raised to the power of y. All I've done on the next line is simply use the third law of indices to express the equation with slightly more clarity. So we have m to the 0, L to the 0, t to the 0 on the left hand side, on the right hand side t to -1. Notice here I have L to the power of 3x, t to the power of -x. I've used the third law of indices to reformat the bracket, and L to the power of 2y. So that's just applying the third law, just to make the equation slightly easier to follow when we equate indices on the next slide. So task 3, solution continued. Just repeated this line here for convenience. So again, I can only generate 2 equations because dimension m does not appear on both sides of the equation. So let's equate the indices for dimension for length L. Left hand side, L to the 0, so 0 on the left hand side of the equation. On the right hand side we have L to the power of 3x here, so that'll be 3x in my equation, and L to the power of 2y, so add 2y. I've stated that as equation 1 here because I cannot solve that. I have 2 unknowns in one equation, so I need to generate another equation. So I've just labelled that as equation 1, and I'll return to that in a moment. Let's now equate indices for the time dimension t. So on the left hand side we have t to the power of 0. So on the right hand side we have t to the power of -1, so -1. And t to the power of -x, so it's my -x on the right hand side. The one unknown, in one equation we can solve that. If we add x to both sides of the equation, we find that x is equal to -1. Now we can substitute the value of x into equation 1, labelled above. Here's the value of x, -1. 3 times -1 will be -3. And add in 3 to both sides and then dividing by 2. Y is equal to 3 divided by 2, or in decimal 1.5. So we can now write the expression as omega q to the power of x, x is -1, a to the power of 1.5. Just note a slight variation here. I could write that as omega a to the power of 3 divided by 2 and divide by q, as q is the -1 means it's reciprocal. And that could further be written as the omega multiplied by a cubed or square rooted, because the power of a half is actually a square root, and then divided by q again. So 3 different ways of expressing the final solution. Most technician students would be quite happy with the first solution. They tend to struggle a little bit trying to generate the third solution, but it's shown there for reference. So that concludes task 3. And purely for reference, here's task 3 showing an alternative solution. In this case, we actually equate the indices for time, t, first of all, and then equate the indices for length, l. Obviously, the final solutions are the same. And here's task 4. A non-dimensional expression this time includes 4 variables. We have rho to the power of x. Rho is actually mass density. We have c to the power of y. C is velocity. We have f, that's force. And we have g to the power of z. G is gravitational acceleration. Answer shown in the bracket. And here's our table containing the various quantities. Mass density shown here, velocity shown here, force and gravitational acceleration. I'll encourage you to start the presentation and attempt task 4, but the full work solution is shown on the following slides. A slightly more complicated solution this time. So here's task 4, the commencement of the solution. As always, consider the quantities given for density, unit, dimensions, velocity, force, and gravitational acceleration, g. So there's the listing of all the quantities considering. As again, this is a non-dimensional expression. The left-hand side is equal to mLt to the power 0, and on the right-hand side we have the mass density raised to the power of x, velocity raised to the power of y, the force, and the gravitational acceleration raised to the power of z. On the next slide, I'll just use the third law of indices again to more clearly express the variables and their associated powers. And that's just for clarity when we equate the various indices on the next slide. So task 4, solution continued. Just repeated this top line from the previous slide for convenience. This time we can generate 3 equations. We have 3 unknowns in our non-dimensional expression, as we can generate the equation for m this time, as we have not in the previous task. So let's equate indices for the mass dimension m. Left hand side it's m to the power 0, so 0 on the left hand side of the equation. On the right hand side we have m to the power of x, so x, and m to the power of 1 here, so add the 1. So one unknown in one equation we can solve directly, so subtracting 1 from both sides of the equation, we clearly see x is equal to -1. Let's now equate indices for the length dimension, capital L. Left hand side we have L to the power 0, so it's 0. The right hand side we have L to the -3x here, so there's -3x. We have L to the positive y here, so we'll add y. L to the positive 1 here, so add 1. And L to the power z here, so add z. We only know the value of x, so that means there are 2 unknowns in that equation, so we cannot at the moment solve the equation generated for dimension L. So I'm just going to label that as equation 1 for reference. So let's equate indices for the final equation in this particular task. That's for dimension time t. Again, on the left hand side we have t to the 0, so that's my 0. On the right hand side we have t to the -y, so -y. We have t to the -2 here, so subtract 2, and we have t to the -2z here, so we subtract 2z. Rearranging the equation for y, adding y to both sides of the equation, y is equal to -2 minus 2z. I've actually called that equation 2 for reference. So now if we substitute equation 2 into equation 1, here's equation 2 substituted into equation 1. Just remove the bracket here and inserted the value of x, because x is equal to -1 from above. So simplifying, Negative 3 times negative 1 is positive 3, and here negative 2 plus 1 is negative 1, shown here. And negative 2z added positive 1z is negative 1z, or negative z, as shown here. So that allows us to solve for z, and adding z to both sides of the equation, we can clearly see that z is equal to 2. Task 4, solution continued. Just repeated equation 2 for reference from the previous slide, and this line here showing that z is equal to 2. We're now going to substitute the value of z into equation 2 shown above, and replacing the z with 2. And when evaluating, we find that the exponent y is equal to negative 6. So we can write our non-dimensional solution in this form of rho to the power of negative 1, because x is negative 1, c to the power of negative 6, because y is equal to negative 6, f for our force, and g to the power of 2, because z is equal to 2. An alternative way of stating this expression is fg squared divided by rho c to the power 6. And that concludes the solution to task 4. Hope this presentation has been of use to you, and as always, thank you for viewing.